please hold your questions after the end of the talk, and when you have them, do come to the mic in the middle. Thanks a lot.
Hi everyone, I'm Jean, and today we're going to talk about how we can have new programming models for making programs more secure. But I'm going to start by saying this is not a talk about a former FBI director, James Comey. I know he's been in the news a lot lately, but this is a computer science talk. It's not going to be about him. What this is going to be a talk about, though, is his secret Twitter account. So how many of you have seen this major headline of how journalist Ashley Feinberg found James Comey's secret Twitter account? Yeah, it was super exciting, right? So normally when you see security in the headlines, it's about these big splashy data breaches or hacks of skateboards or rifles or ransomware of all of England's health records. But what you don't see a lot is these subtle chains of information leaks leading to major headlines. So this was really exciting for me because I work on information flow security, and so I will talk about what happened here and how why this is a very big deal. So it all began when journalist Ashley Feinberg couldn't resist the challenge to find James Comey's secret Twitter account. So James Comey, back when he was still FBI director, said that he's on Twitter, but he didn't tell you what his Twitter handle was. And he's on Instagram with 9 followers. And so Feinberg said, I wonder how long it's going to take me to find the secret Twitter account, especially since, FBI Director James Comey has some tricks up his sleeve. He probably knows how to protect that account. So she started by scouring Twitter for mentions of his son. And Twitter now has very nice search interfaces. You can search Twitter for a lot of things. So she knew if she just searched for James Comey, there's too much stuff. But his less famous family members. So she searched for, I think it was Brian, which is his son's name, minus James Comey. And so she found a mention of his son on Twitter. It happened to be a post from his college, Kenyon, so his son is a university student. And he was playing some kind of sport, and there was a picture with an associated Instagram post. And so this Twitter post linked to an Instagram post, and it said, they're teeing off with Brian Comey. And now this Instagram post didn't even link to Brian Comey, it just said his name. But enough things checked out, she knew that the son went to Kenyon. But then she went and looked in the comments of the post and found someone saying, at Brian Comey, congratulations, great job. And this is how she found Brian Comey's Instagram account. And the next step was to follow the son on Instagram. And you might say, well, Jean, there's nothing really interesting here with respect to any kind of bugs. Why are you telling me all this? But what I'm going to tell you next is that there was a key information flow bug that Ashley Feinberg was able to exploit in Instagram. And this is how Instagram revealed James Comey. So Ashley Feinberg goes to follow Brian Comey, and he is James Comey's son, so he has a protected Instagram account. And then in the suggestions, there shows up a bunch of Comey family members who all use their real names, and then this very mysterious Reinhold Niebuhr. So it turns out that Reinhold Niebuhr is the name of the theologian that Comey wrote his senior college thesis on, and 9 is exactly the number of people James Comey said that he was following. And this checked out, so it turns out James Comey is not so sneaky. He uses the same very creative anonymous handle on Instagram as he does on Twitter. There are some very key important people following Reinhold Niebuhr on Twitter who don't just follow everybody. And so this is very likely James Comey's Instagram account. This is very likely James Comey's Twitter account. And now let's talk about why this wasn't just about Ashley Feinberg being clever, but why this was about Ashley Feinberg exploiting an information leak in Instagram. So what we have here is the suggestions that Feinberg got were very likely based on follow information. But on Instagram, the follow information should be kept secret in a protected account until the follow request has been accepted. And so what happened here was that Instagram has this, they don't have an explicit contract, but when you go to someone's profile, if you're not following them yet, then you shouldn't be able to see their photos. You shouldn't be able to see who they're following. But what's happening is that Instagram is allowing this information to leak through recommendations. And in fact, also in the spring class I was teaching, one of the students made $1,000 from the class because Instagram was also leaking secret photos through email alerts. So they sent an email saying, please come back on Instagram. Here are all the photos you can see. He saw, this student saw some private photos of his high school wrestling coach. He said, oh, cool, let me click on that. Went to click on it. He's not actually supposed to see these photos. And so the fact of the matter is, when you just are viewing these Instagram accounts through the profiles themselves, it's fairly easy to protect this information. But when you have search interfaces, when you have email updates, when you have recommendation algorithms, all this becomes a lot harder. And so in this talk, I'll first talk about what is information flow and why is it so difficult to get right. Then I'll talk about my work on factoring out information flow policies from the rest of the program. And then I'll talk about, well, we have all of these nice solutions for protecting these information flow policies within an application runtime, but in real applications, we interact with databases, and so what about the database? And then finally, all of the things I'll tell you about in the beginning of the talk is based on a dynamic runtime approach. There are overheads when you do something completely at runtime, so I'll talk about our ongoing work about how can we throw these runtime overheads away. So the main contributions that I'll describe include a runtime approach for policy-agnostic programming for information flow that we've implemented as a embedded domain-specific library in Python and as a web framework built on top of Django. And then our static policy-agnostic system is built on top of Liquid Haskell and a system called Lifty, and we're also currently working on Bina, which is a policy-agnostic web framework built on top of the Yesod framework in Haskell. All right, so I'll start by talking about what's information flow and what's hard. So the problem that we saw with this Instagram example is that implementing checks and filters across the program is error-prone. So on Instagram, you have your follow list, you have your follows of follows, you have what's hot on Instagram, and they're all being fed to this recommendation algorithm, and they're supposed to be shown to people like Ashley Feinberg. But what happened here was we had a missing check. Your follows list should only be visible to the followers. And one can imagine if they missed a check there, probably they also missed a check that follows of follows should also adhere to individual policies. And in some ways, we really don't blame the programmers because it's very easy to accidentally leave off some check on some piece of information that you're feeding to a recommendation algorithm to make sure that all of the information is being shown as it's supposed to. And we can imagine that it gets even more insidious with a fancy recommendation algorithm. So you can imagine that there are, in the future, or even now, you have all these programmers implementing all these heuristics for what should get recommended to someone for who they follow, and only one of the rules is whether the other user is a member of some follow list, then you add them to the recommendations list with some score. Here we have 4. And here it's particularly insidious because the other user's profile and all that information may be public, but the fact that they're getting added to the recommendation list based on follow information is what's secret. So this is what's called an implicit flow with information flow. So your check that determines whether some public information is being added to a list is what's protected, but the actual information going out of the system, a list of usernames and profile pictures, something like that, that's actually all allowed to be seen. And so in order to make sure that these kinds of leaks aren't happening, you really have to track how information is flowing across the program, so how all of your results are being computed. And then, of course, there's the potential that other user might have its own policies. So in order to make sure that information flow policies aren't being violated, the programmer has to track how values are flowing through the program and also what the associated policies for all these values are. And there are many ways that information flow bugs can leak secrets. So recommendation algorithms, as I mentioned, are just one of them. Search interfaces are super dangerous. So if you've seen a lot of these papers about information flow, a lot of them go something along the lines of, in the hot crap conference management system or some other conference management system, since conference management systems are the one piece of software that paper reviewers are guaranteed to have read, there's a search interface, information leaked this way. And also, basically, anytime code does anything interesting with secrets, there's this potential that the interaction of sensitive data with the code can leak information. And this isn't surprising, because the challenge we have to deal with is what people call policy spaghetti. So here I show two screenshots of code from the hot crap conference management system, which, as I said, is the canonical case study for a lot of information flow research. And what I did one day was I looked at all of the code that is associated with policy checks, and I've highlighted those here. And so these are checks that look at things like who is the viewer, are they a reviewer, what's their role in the conference, and also things like what phase of the conference are we at right now. And then all of the code in between is showing different values based on these conditions. So what you have is these conditional access checks intertwined with other code. And on the left here, you see the checks are actually dominating the code. On the right-hand side, there are actually dynamically generated SQL queries. So these checks are not just determining what you're showing, but they're also determining computations that you're doing interacting with the database. And anytime you want to implement a new policy, anytime you want to implement new code, anytime you want to fix a bug, the programmer has to worry about this interaction of policies with other code. And here I'm just showing two files, but in at least 24 of the 82 files I looked at, the code looked something like this. And yeah, looking at this code, it was really not surprising that there are often bugs whenever policies are changed. And there's the additional challenge of what happens when policies themselves get fancy too. So if you've been using Facebook, you probably are seeing a trend towards really fine-grained stateful policies, like only my friends can see my location between 2 p.m. and 4 p.m. on Wednesdays. So we're not quite there yet, but you have these policies that really depend on current state and also relationships between users. You can have policies that talk about the sensitive information they're protecting, like only people near me can see my location. And also policies that might depend on multiple things, like only authors of accepted papers can see the accepted paper list, but only after some final decision has been made. So you can imagine if you only kept track of the first part of that policy, you could accidentally leak accepted paper information before final decisions have been made, or something like that. And so policies might depend on sensitive values, including the values they're protecting. Policies might depend on a lot of other things. The programmer has to keep track of all of this right now if they want to get things right. And the policies that depend on sensitive values is a particularly tricky one, because the current state of the art involves resolving these policies in some kind of omniscient context. Because how are you supposed to get at sensitive values without having full access to them? And so in this way, policy dependencies, programmers are trusted to handle these policy dependencies right now. And then there's also an additional challenge. So if you recall the code I showed you before, there are many cases, each of which determines a different possible view of the data. So there's also the challenge that we want our software to demonstrate reasonable behavior. We don't just want, if a check fails, to show 404, we can't show you anything, but actually what you want is this differentiated behavior of your software depending on different policies. And right now, the programmers are responsible for implementing the functionality for what should happen if each check fails. They're responsible for implementing all the cases of what needs to happen corresponding to each situation. And so now you might say, well, Jean, people have been doing work on information flow for decades now. Why haven't they addressed all these problems? And what I'll say is that other approaches deal with the correctness problems when it comes to information flow. So they'll prevent programs from leaking information, but they don't address the problem of programmer bottleneck. So there have been static label-based approaches that let you label data, and they'll prevent your program from compiling if sensitive data is leaking to users in any kind of significant way. There have been dynamic label-based approaches, which will let you label your data and then at runtime track that information so that if your program at some point accidentally tries to leak information, it'll stop your program, either by raising an exception or silently failing in some way, for instance, not showing a certain piece of information. And then there are secure multi-execution approaches, which will spawn two threads. One for each sensitive value that gets used, one for each other value, and this way, by construction of how it's executing the program, guarantee that secret values won't go where they're not supposed to go. But in all of these approaches, the programmer is trusted to encode these high-level policies as low-level labels about, for a given viewer, can they see this value? Yes, no. So you have these super stateful policies, like only my friends can see my location between 2 and 4 p.m., and you have to, the programmer is trusted right now to translate that down to Alice is trying to view my location right now, is she allowed to see it? The programmer also needs to implement conditional access checks across the program still. So these approaches will check that your program isn't leaking information, but someone still has to make sure that the program is constructed correctly, otherwise the program won't compile, or there's going to be some kind of behavior at runtime that a runtime monitor will stop. And the programmer is also responsible for implementing alternate behavior for when these checks fail. So in the other cases, unless the programmer just wants some kind of 404 error or some kind of other silent failure when the program is running, the programmer needs to make sure, okay, I've handled all these cases. And so while all these approaches before provide really nice infrastructure for specifying what it means not to leak information, and they will prevent your program from leaking information, the programmer is still responsible for making sure that the program gets constructed in a way that something useful is happening while the program runs. So in short, existing approaches prevent bad programs from running, but it's still hard to write these good programs. So to summarize the challenges so far, we have this issue of policy spaghetti providing a programmer bottleneck, and other approaches only providing emergency brakes. So as more and more programs deal with sensitive information, every single programmer has to worry about information flow all across your program. This is really holding programmers back. Policies might depend on other policies, and trusting the programmer to manage these dependencies can lead to leaks. So if you imagine programmers already have to deal with policy spaghetti, but they also now have to deal with policies getting more complicated. Am I dealing with all the policies correctly? Am I dealing with all of the dependencies between policies correctly? This is becoming increasingly challenging. And there's also the problem of specifying what happens when policies fail. So if you remember from the policy spaghetti code, there's just all these cases that programmers currently have to handle. And so if you've written this kind of code, you might be saying, yes, I recognize these problems. If you haven't, I encourage you to try writing a web application with some kinds of policies, and very quickly, you might say, oh my gosh, most of this web code is actually policy code. And so now I'll talk about our proposed approach for factoring out these information flow policies from the program. I'll first talk about the dynamic semantics for this approach, which is the runtime solution we have for this. I'd like to say, though, that we now think of our dynamic semantics as a reference semantics for how to think about programs this way, but we've since done many optimizations on this, and we also have a static program rewriting approach to get programs to adhere to these semantics. So, right, so bear with me in this part. But the goal here really is to factor out information flow policies from the code. So what we want is to allow programmers to implement their recommendation algorithms just as these functions, where we have code like if is member, other user follow list, we add the other user to the recommendations algorithm. We don't have to worry about implicit flows. We don't have to worry about what the policy is on other user. We can just implement search functionality, recommendation algorithm functionality, all kinds of other functionality without worrying about the policies. So the goal is to have programmers just write this policy-agnostic code without additional checks and filters, and for the compiler and runtime to be responsible for checking policies and handling alternate executions for when policies fail, or the checks fail. And our main insight is to encapsulate policies directly with the data and have each sensitive value contain an alternate default value that should be used for when the policy check fails. So in our system, we have these values called faceted values that contain a high confidentiality secret value, a low confidentiality other value, and then an associated policy saying when a viewer should see the secret value versus the other value. And these values can now be used, and policies are Boolean functions that take a viewer as an argument and return whether the viewer is allowed to see the sensitive value. And policies are allowed to depend on sensitive values. And now these faceted values can be used as regular program values throughout the program. You can just insert this faceted value into your recommendation algorithm function now. And these evaluation of faceted values yield more faceted values. So what happens is if we do a conditional check with the faceted value, what we get is a faceted conditional. And then according to our semantics, the runtime is now responsible for keeping track of what assumptions it had to make to go inside a conditional branch. So if you're doing a conditional based on a sensitive value, it keeps track of, okay, this was the policy that needed to be satisfied in order to have gotten here. And if we update something inside of a conditional, that update now gets tagged with the same policy. So here the recommendations list becomes the previous recommendations list with other user 4 added to it, or just the previous recommendations list guarded by the same policy that guarded the follow information. And the machine is now responsible for handling policy dependencies too. So we can have a policy that says the viewer needs to be a member of the follow list in order to see the follow list. Maybe the follow list is visible if another secret field has value X. What we do is we introduce labels to guard the faceted values. And these policies, these labels allow policies to refer to each other. And now the compiler and or runtime is responsible for solving for values of labels depending on the policies. So before, with the label-based approaches I told you about, the programmer was responsible for explicitly assigning the label values. Now you can think of the labels as free Boolean variables that the runtime or compiler is responsible for figuring out the values of based on the policies. And more concretely, how the labels get assigned from the policies is as follows. So let's say we have this function mapping to label A. So we have a function followers can see that takes a viewer and says that the viewer can see label something guarded by label A if it's a member of the follow list. What happens is we keep track of these policies until there's a viewer. And so now Ashley Feinberg is trying to view something. So we create a constraint based on the viewer that says if Ashley Feinberg is a member of the follow list, that implies that our label A has to be high. And then we can figure out more specifically what this means. Ashley Feinberg at this point is not a member of our follow list, so we get false implies A equals high, which means that A is low, and Ashley Feinberg shouldn't be able to see our whatever this label A is guarding. And so in this way, the labels make sure that all policy dependencies get satisfied. And so what we have so far is the faceted execution makes sure that any computation that depended on a sensitive value is now tagged by the policy associated with that. And how we're handling the labels makes sure that all of the policy dependencies get taken into account when the values are actually shown. And what we've done is we've modeled this very precisely using operational semantics of the runtime. And we've proven a security guarantee about what it means to show values in our language. And so to give you some background about our security guarantee, I'll first review what traditional non-interference means. So traditionally in information flow, there's this idea of non-interference, which says that a non-privileged viewer should not be able to tell the difference between any pair of sensitive values. So if you have a sensitive value going through the program, like this sensitive list of who Brian Comey is following, that list, if the viewer is not supposed to see it, can contain Reinhold Niebuhr, it can contain Miley Cyrus, and the viewer shouldn't be able to tell apart the difference between those two lists. There's a tricky part of our language, though, which where the policies themselves might depend on your sensitive values. So here we have, you could have a policy that says you have to be in your list of followers to see that list of followers. And so resolving that policy itself reveals some information about that list of follows. And so how we handle this is we have a modified non-interference theorem that says that a non-privileged viewer shouldn't be able to tell the difference apart between any pair of sensitive values that doesn't give the viewer privilege. So how you can understand this is that the space of sensitive values is split into two parts. There's the part of sensitive values that would give a given viewer privilege, and then there's the space of the sensitive values that doesn't give the viewer privilege. So for the followers list, there's all the follows list that Ashley Feinberg is a part of and lets her see the list. And for those, she can definitely tell them apart. And then there's the space of follows list that Ashley Feinberg can't see, which is all the lists that she's not on. And so what our modified non-interference theorem says is that Ashley Feinberg, as a non-privileged viewer, can't tell the difference between any of the space of lists that she's not on. And so what we have now is this. So far I've told you about a language that allows programmers to attach policies directly to data. The labels don't get assigned by the programmer anymore, but they get assigned by the runtime. The runtime is responsible for propagating policies and sensitive value information through the entire program, and the runtime is responsible for managing the dependencies of policies on each other. And so what we did was we came up with the semantics, we implemented a version in Scala, then we implemented a version in Python, and we said, very cool, we have these nice guarantees, let's try to build web applications with them. We started building a conference management system in our Python system, or actually first in our Scala system, and then we realized, oh wait, all realistic applications have this interaction with SQL databases. And we had all these nice guarantees, but as soon as we call out to the database, all of our guarantees go out the window because our database doesn't know about our policies. And so let me first start by talking about some of the dangers of interacting with vanilla databases. So what you have here is what you could potentially have is in your database, you have all this data. You might want to do a query based on a search interface or a recommendation algorithm that says, select everything from users where the location is equal to Sagrada Familia, and you want to show this to Ashley Feinberg. And what you have here is potentially an implicit flow. So your database doesn't know that your location might be protected. You select based on this sensitive location value. Maybe your user's information is actually public, like I said before, but the fact that you selected based on this sensitive value leaks information. And so the high-level takeaway is that database queries can leak all sorts of information that they're not supposed to leak, anytime your program has a call to the database, that call needs to be aware of the policies, unless you have some kind of strategy for dealing with this. And because our whole thing before was that we were factoring all your policies in your code, you don't need to worry about the policies. Requiring the programmer to reason about policies when calling out to the database is not really acceptable based on our claim before. And so what you can say now is, well, we can just take all the data in our database and load it into our runtime, because our runtime has really nice guarantees, so why don't we just rely on that for our properties? And most of you might know this is not so practical. You can't always load your entire database into memory. You're not leveraging all of the decades of optimization that's been done on SQL, etc. And so the challenge here for us was to support faceted execution when interacting with an unmodified SQL database. And people said, well, why do you care about interacting with an unmodified SQL database? You're making a whole new programming model anyway. Why not just make a whole new database? But it was really important for us to be able to interface with unmodified SQL, because we figured if we're requiring programmers to pick up a whole new database as well, this approach is just never going to get adopted. So what we wanted here was faceted queries on an unmodified database. And the semantics that we wanted was for the programmer to be able to call save on a faceted value, write that to a SQL database, have the database store a conceptual row that maps a primary key to some faceted value, and then when they do select everything from users where location is equal to Sagrada Familia, they get a result back that contains faceted values protected by the policies so that implicit flows aren't happening. And there are some naive ways of doing this. So first we said, okay, why don't we just store facets in our database as strings? Or maybe we can use a new database for each label. But neither was super appealing, because these ideas are either too expensive or make it difficult to extend the formal semantics. And in fact, many of our ideas had both problems. So if we store our facets as strings, there's really no way to query inside the facets, and also that makes extending the semantics a nightmare. And so our solution was to use the object relational mapping to map facets onto multiple database rows. So our key insight here was that, well, people are already using object relational mappings to maintain uniform object representations between an application and a database. Why not use an object relational mapping to maintain a uniform facet representation and all of the invariants of these faceted values? So what we can do, and the specific representation matters because it determines how much of SQL we actually can use. So what we did was we took a conceptual row, we mapped it onto multiple database rows with metadata about the labels. So for this location with primary key 1, we have an additional column that stores the Jeeves key, and that ties together all the rows corresponding to one facet. And then we have an additional metadata column, labels, that says which facet each row corresponds to. And now when you do the selection, you'll just get the subset of the rows that actually match on the value, but if you make sure that the ORM defacets appropriately, then what you'll get as a refaceted value is the same policy associated with either the location value, which is sensitive, or the empty list of rows. And it turns out that this multiple row metadata way of storing values allows us to reuse SQL infrastructure for get, all, filter, sort, and foreign keys. So it turns out that because you have these faceted values just sitting in the database, and if you have this additional property that you're handling the metadata correctly, you don't actually have to change the way you're doing get, all, filter, sort, and foreign keys. You just have to make sure you're writing the facets to the database in the correct way, and that you're reattaching labels back in the correct way. Aggregation is a little trickier because if you sum across all your rows, you'll just get everything, so that has to be implemented in a special way. But we were able to not only use this approach to extend our guarantees in a clean way, but we were able to build a practical web framework based on this. So in a standard web framework, you have a model, view, and controller, where the model describes the data layout, the view describes how the front end should be laid out, and the controller describes everything in between. What we have in addition now is the programmer specifies policies directly associated with the data model. The controller runs in an enhanced runtime. The framework attaches policies based on the annotations with the model. There's an ORM that propagates policies and sensitive values across the application and database. And then the framework shows the appropriate values based on the viewer and the policies. And there's an additional nice part, which is the framework usually keeps track of the session user anyway, and most of the time, that's your viewer. And so to give an example of policies in Jacqueline, here's what you would normally write for in Django to specify your data model. You have a user profile, you have an email field, it's just a character field. So now we have this additional, so this is actual code from our web framework. So now you have this additional function you define for the default value, Jeeves get private email, that takes the current row user, and it's not using that right now, it's just returning the empty string. And then you define an information flow policy in terms of your current row user and your viewer context. And here, this is a snippet from our conference management system. So you're returning whether the current row is equal to the viewer or if the current viewer is the chair of the conference. Then they can see the user email. And in Jacqueline, we have centralized policies now, so all of the policies are in one place associated with the model, and you no longer need policy code in the view or the controller. And I said before that the framework can now keep track of who your viewer is, and this allows us to do a very key optimization, which is we can make the observation that the framework can often, but not always, track the viewer. And so this allows us to explore fewer paths. So you can speculate that the session user is probably going to be who's viewing it, and you don't actually have to do this multi-execution. You can just throw away your executions, and in the case where you're doing something like send email to everyone in my guest list, then you can go back and do the expensive thing. So we did some application case studies. We built a small course manager, a health record manager, and a conference management system that we deployed for a small workshop. And what we showed was that Jacqueline reduces the number of lines of policy code, makes the code centralized so it's much easier to audit, and it also yields reasonable overheads. And so we did some stress tests where we increased the number of papers in our database, and we looked at the time it took to load a single paper and to load a list of all papers. And it turns out for a single paper, Jacqueline is actually faster than a version with manually implemented policies in Django, because for that you have to check each policy, whereas here the policies in Jacqueline, the policies get checked all at once. And then for all papers, there's 1.75x overhead, because the faceted execution does have some overheads in our Python implementation. And these overheads motivated our ongoing work, which I'll tell you very quickly about, but it involves static type-driven repair for policy-agnostic programming. So if you look on our website, which I'll show at the end, we have more information about this, but basically the high-level idea is we encode the policies as refinement types, types that can depend on program terms. Specifically, we encode these policies as liquid types in liquid Haskell, so liquid types are decidedly checkable refinement types. We use type error localization to figure out where to insert policies in the program, and the decidability is key because the error localization is also decidable now. And then once we figure out what the holes are, it's a very easy synthesis problem to turn each hole into a check. And so what we have now is this procedure that is taking a program where types, where each policy is specified once as a refinement type, and it's the compiler is figuring out where to insert checks and what checks to insert. And we're currently working on building a web framework based on this. And so a summary of our contributions is we've developed a dynamic semantics for policy-agnostic programming, we've extended this to database-backed applications, and we've been working on static type-driven repair to support this approach. The main takeaway from this is that factoring out information flow policies is not only possible, but reduces the lines of policy code necessary and also has very reasonable overheads, especially if you're doing a static program rewriting approach. And I hope I've convinced you that as we have more code that deals with sensitive values, it becomes really important to factor out security and privacy policies from the code. Two things I'm really excited about for the future are doing this for statistical privacy and also using this approach for information flow for securing legacy code. And I'm very excited that we can even think about factoring out information flow and other policies in this way. And I'm very excited to think with all of you about how we can make these policy-agnostic approaches practical in the next few years. Thank you.
Okay, so I think we have time for 1 or 2 questions. And if there are none, then I think let's thank the speaker again, and let's meet here in 10 minutes. Oh, there's a question. Oh, sorry.
What are the problems in observing the performance of a large data set?
Oh, sorry?
One of the problems is that things are observable because it takes a long time.
Yeah, so the question was, there's a problem with things taking a long time in a large data set. So this is a problem that people are addressing. So these are timing channels problems. There are solutions where people pad computations so that everything takes a long time. One might say this is not the most desirable solution, but there are ways where you say, okay, if all computations take the same amount of time, then we're not leaking additional information. And that is a kind of channel that could be potentially incorporated into an approach like this. But yeah, good point.
Okay, so thank you.